So in this video, we're going to look at Kirchhoffs' two laws. They're very simple laws, but they're extremely profound, and you'll use them to solve all kinds of problems, not just at circuits at this level, but all of the circuit problems you solve, even as they get much more complicated. Almost any circuit can be solved with some pretty simple rules. And there's two of them. The first is Kirchhoffs' current law, which is that the sum of all the current flowing into a node is equal to the sum of all the current flowing out of the node. So first, what do I mean by a node? Think of a node as like an intersection in the road. So this right here is an intersection. You have some current that flows from the battery. Remember, we use conventional current, so we pretend that positive charges move, even though they don't. So we pretend that current is moving away from this positive side, and it's coming this way towards this intersection. Well, then some of the current will go this way, right, and some will go this way, and then it'll kind of loop back, right, like this. And here's another node, another intersection. It'll meet up again here, and then go back to the battery, and that will be the direction that the current flows in this circuit. So these points right here, these are nodes or intersections. The idea of Kirchhoff's current law is that whatever flows into a node has to be what flows out, and it makes a lot of sense. I like to think about the analogy of current as being like counting the number of people walking along a path. So in this example here, the current coming from the battery, we're saying is 5 amps. So let's think about that as like 5 people are walking along this way. And then at this intersection, well, they're going to split up. So if 2 of them go this way, so the current through this resistor here is 2 amps. So we'll say I2 is 2 amps. It's the current through resistor 2. We keep our subscripts the same that way. So the current through resistor 2 is I2. And let's just say that was 2 amps this way. Well, then that actually tells us how many people must have gone through resistor 3. Right? It's the rest of them. If 5 amps went this way, 2 went this way, then everybody else must have gone this way. I3 will have to be the current from the battery minus I2, and that's going to be 3 amps. Oh, sorry, forgot the 3. There we go. So 5 people walk into this intersection here, 2 go this way, then there must be 3 going this way. And let's keep going with this, right? So these 3 people come along here, right? These 2 people come this way, then they're going to meet up at this intersection. So again, we can use our current law to say, well, 2 people are coming into the intersection from here, 3 people are coming in from here, so how many people must go on? Well, it must be 5 people. So I1, which is the current through this resistor, must be 5 amps again. And that really makes sense because those 5 amps will follow along here, and people can't just sort of fall off the path. They're all going to be right here too. So if there was 5 amps coming into this intersection here, it makes a lot of sense that 5 amps must have been along this path up here through resistor 1 as well. So that is Kirchhoff's current law. The current flowing into a node is equal to whatever current is flowing out of that node or intersection. The other one of Kirchhoff's laws is the voltage law, and that's the idea that around any closed loop that you draw in your circuit, the change in electrical potential difference is 0. Now this actually works around literally any loop, so you could draw like this loop here, but you need to use a few special techniques to do loops that are not including the battery, so we're not going to do that in our course, but in the future, just know that this law is actually generally applicable. It works for any closed loop, not just ones that include the battery. But we'll use ones that include the battery because that gives us kind of a baseline. So let's say this battery is a 12-volt battery. So we'll say delta V at the battery, so we often call that maybe a B for battery, or sometimes total is common as well. So that's 12 volts there. So that means that at the battery you gain a height of 12 volts, and then you're going to be coming along through this orange loop here. So when you get to this intersection, you have to choose which loop you take. Think about it as a roller coaster. You gain 12 volts of height here at the battery, and then you could either go along this path and come back to the battery, but you have to lose all your height if you go along that path, or you could take this bigger path and go back to the battery. So you can pick one of those 2 loops, and that'll be what you go down. Let's say you pick the orange loop, and let's imagine that your delta V2 here, say 4 volts. So what that means is that we gain 12 volts at the battery, and we've lost 2 of them going through R2. Well, by the time I get back to the battery again, I have to lose all of the energy that I gained from the battery. I have to lose all of the voltage. So that means that delta V1, the voltage across this resistor here, has to be 8 volts, right? I've gained 12 of the battery, I've lost 4 so far, I need to lose another 8 in order to get back to the battery again. Now, that's for the orange loop, but what if I want to do a bigger loop? So what if I want to gain the 12 volts of the battery, and some of the electrons, or we pretend it's protons, that move around the circuit are going to go this way, right? They'll take this broader loop. Notice that these electrons don't even go through R2 at all. They're just going to go through R3 and R1 and the battery. So along that bigger loop, you gain 12 volts of height at the battery. You're going to have to lose something at R3, and then we're going to lose the rest at R1, and we've already figured out that the voltage across that resistor is 8 volts. So if I gain 12 volts of height here, and I have to lose all 12 volts by the time I get back to the battery, I'm going to lose 8 here. Well, R3 has to have a potential difference of 4 volts as well. And that should fit with what we talked about with parallel circuits, that the potential difference across resistors that are in parallel with each other has to be equal. So it doesn't have to be the same as R1, because R1 is not in parallel with R2 and R3, right? But R2 and R3 have to have the same voltage drop as each other because they're in parallel with each other.